Okay, so let's move on to activity 4. So far, we've been discussing the relationship between vibrational frequencies and force constants and reduced masses. We've been looking at how we can determine a fundamental frequency. We've been seeing that for most molecules, these are on the order of several hundred to a couple of thousand wave numbers. We then, on the previous activity 3, we're just looking at rotational constants, seeing they're in the order of about 2 to 20 or so wave numbers. So much smaller in magnitude than the vibrational frequencies. And so the energy it takes to rotate molecules, very small, doesn't take much energy. Takes a little bit more energy to cause vibrational energy changes in molecules. And then, of course, even greater energy to move electrons around or to break nuclei in terms of changes in electronic state or the nuclear state of the molecule. Now, within this activity here, what we're going to be comparing is, and really trying to get a glimpse of, is what are the fraction of molecules that exist in some higher energy state compared to some lower energy state. And so the first part, we're going to compare the fraction of molecules in V equals 1 compared to V equals 0. So how many molecules are vibrationally excited within an ordinary sample of a substance? Now, the answer is probably going to be not many, just to give you a glimpse of what you're probably going to find. Now, the dependence here is on the vibrational energy. So how much energy does it take you to go from V equals 0 to V equals 1? So that difference of energy, I don't know why this is appearing so weird in terms of the appearance, but the difference between V equals 0 and 1 is going to be our vibrational energy, difference of energy. And so then you can plug that energy in, use the Boltzmann's constant. Now, if you look on the opening page of the experiment, we have various units for KB. One of them is in wave numbers per Kelvin. I would recommend using that value and treating your vibrational energy here in units of wave numbers. So just use the KB in units of wave numbers per Kelvin if you're using your vibrational energy in units of wave numbers. You can convert everything over to inverse seconds, but I wouldn't bother with the conversions. It's simple enough to use the units in units of wave numbers. And then that'll allow you to calculate in the first part of the activity here the I really don't know why this is doing what it's doing. Why the pen looks so weird. But so then the you can solve for HF, HCl, CO with the fundamental vibrational frequency from page 4. Solve for the fraction of molecules that are V equals 1 compared to V equals 0 at 10 Kelvin, 100, 300, and 1,000. So you can see as you're warming a sample up, you're going to be populating more and more molecules in V equals 1, but not really ever that large of a percentage. And then the second part, and this is going to require to use Excel because there's going to be a lot of calculations that are involved here, but the second part would be using the B0, the BE and alpha E with equation 16. So that's just relating BE and alpha E to B0. So solve for B0. And then within the Excel spreadsheet, try to solve for the first, say, 50 rotational energy levels. This is going to be a lot of rotational energy levels, especially for a molecule like carbon monoxide that has a relatively small rotational constant. But solve for the fraction of molecules that exist in J equals 1, 2, 3, etc. compared to J equals 0. And the issue here with rotations is we get this degeneracy factor that's a function of J. The degeneracy is 2J plus 1. So the degeneracy is sort of how many ways are there distributing, or like what's the degeneracy of states that have a J of 1 versus 2 versus 3. And if you plug in a 0 for J, you see it's 2 times 0 plus 1. So there's only one way to have no rotational energy. But if you have J of 1, 1 times 2 plus 1 is 3. So like 3 ways to have one quantum of rotational energy. There's a degeneracy of 5 for J equals 2. So what you have is a degeneracy or a state weighting factor that's going to help some of these higher rotational energy level states become more occupied at even reasonably low temperatures. Okay, so what we can do is we can plug in our rotational energy here. Use your F of J here as your rotational energy in units of wave numbers so that you don't have to do a lot of converting over to joules and then using a Boltzmann constant then of joules per Kelvin. So you can use the Boltzmann constant as either joules per Kelvin or wave numbers per Kelvin, but then just match it up with the energy units so that you're taking the exponential of a unitless quantity as you should. Okay, so what you should find is that you're going to have, at least at the higher temperatures, a weighting of states that's higher in the higher J states that eventually starts to drop off as you go up in J values. So what you're going to end up seeing is that you get a sort of an increase in the population, then eventually a decrease. And then this is going to start to look like that spectrum that we're seeing of HCl on that previous page, where you're going to get a relative population of the different rotational states through the picture that you're getting with the IR spectrum. Okay, so what we're going to do is go to Excel, and I'll probably put up a second video later of showing how to use Excel. I actually need to do that with a computer as opposed to the iPad with a pencil, but I'll go ahead and show a separate video of how I might set up a spreadsheet to solve for these state occupations. But what we're going to find is that it's going to be the most occupied value is probably not going to be J equals 0, as long as we're at some reasonably high temperature. Okay, so I think that's all for this video. Thanks for the attention.